Good morning, everyone. My name is Dr. Sam Peavy, for those of you that don't know me, and I'm a professor and chair of the Geology and Physics Department. It's my pleasure today to welcome Dr. Heather DeShon. Dr. DeShon comes to us from Southern Methodist University in Dallas, Texas. She's an associate professor there. Before that, she was at the Center for Earthquake Research and Information in Memphis, Tennessee at CERI for a number of years. And Dr. DeShon has a bachelor's degree from SMU in geophysics and mathematics, a PhD from the University of California at Santa Cruz in geophysics. She also did a postdoctoral research at the University of Wisconsin. And her research is focused on things like subduction zones and also intraplate earthquakes. She's done some work on the New Madrid seismic zone in the central United States also. She's also worked on volcanoes. I saw several publications on the Augustine volcano in Alaska. So she's done all kinds of interesting research. And she's going to tell you a little bit today about great earthquakes and new insights into subduction seismogenesis. So let's give a warm GSW welcome to Dr. Heather DeShon.
See, I am turned on. Well, thank you all for having me. I come hosted by the university, but also hosted by the GeoPRISMS NSF Directorate, and this is it's not a directorate, it's a program, the geodynamic processes at rifting and subduction margins. So today I'm going to talk to you about great earthquakes and what we've learned from the recent series of earthquakes that kind of started in 2004 with the Sumatra earthquake. But first I wanted to put up this quote. "The earth, the very emblem of solidity, has moved beneath our feet like a thick crust over a fluid." Now this was an observation made by Charles Darwin. And when he was on the voyage of the Beagle in 1930s, like early 30s, he was in Chile when this large earthquake occurred in February of 1935. And in fact, Charles Darwin experienced a great subduction zone megathrust earthquake. We estimate now that it was a magnitude 8.5. We're going to talk about a very similar earthquake that happened in Chile more recently in 2010 in almost the same area. But I like to put this up because this observation of Darwin's in the 1830s really speaks to an insightful concept that doesn't really get developed into our idea of plate tectonics until the late 1950s and early 1960s. So here's a brief outline of my talk so you know where I'm going. As we get there, I'm going to start with an overview of subduction megathrust faults and define my term, the seismogenic zone. So this is what we're going to be talking about today. We're going to be talking about let's see if I can be specific here. We're going to be talking about the plate interface between the subducting oceanic lithosphere and, in all of the cases today, continental upper plate. So this region where the plate interface is locked is going to be termed the subduction megathrust fault. And we're going to be talking about earthquakes where this locked fault breaks and the subducting oceanic plate is allowed to further its way down into the mantle and the upper plate is going to pop upwards. I'm going to spend a little bit of time just talking about the GeoPRISMS program. And in particular, why NSF is interested in subduction zone earthquakes. And an initiative in the GeoPRISMS program is subduction cycles and deformation. I'm really going to use this just to outline one or two outstanding questions that the seismology community is interested in. We consider these grand challenges in seismology, and we still don't know exactly how fault processes work. And then the meat of the talk is going to be a bit of seismology tourism. We're going to start with Sumatra and work our way through these magnitude 8 or greater earthquakes that have happened since 2004. And I'm really just going to hit on a slide or two for each earthquake, really emphasizing what those earthquakes taught us about subduction megathrust faults that we didn't know. I'll move on to some future concerns and then present a few insights and a new model that everyone in the community likes but still needs a lot of testing. So future work. All right. First, I just want to make sure everyone's on the same page when it comes to the background of plate tectonics, and I want to talk a bit about our active Earth. So this is a screenshot from the IRIS seismic monitor. So IRIS stands for Incorporated Research Institutes for Seismology. It has a nice education and outreach website, and one of the things it provides is this seismic monitor. So this gets updated by the minute. This shows earthquake occurrence throughout the world, minute by minute. Just to go over the legend here, the pink dots represent earthquakes that have occurred just in the last 5 years, and these are earthquakes magnitude 4 and above. The yellow earthquakes are earthquakes within the past 2 weeks, and the size of the circle is scaled with the magnitude of the event. Then we get to the orange, and the orange and red might be hard to distinguish from the back of the room, but the orange are earthquakes that occurred yesterday, or in this case, the screen's capture is from February 20th, so events that had occurred on February 19th, and then the red circles are the earthquakes that had occurred within the past day when I captured this screenshot. So as you can see, earthquakes occur all the time, right? Some earthquakes are big enough to affect society and make the news, and we become more aware of them, but earthquakes are in fact very common. The earthquakes in general define what we know now are tectonic plates, where we have rigid lithosphere riding on top of a convecting mantle. So hopefully everyone has seen this at some point in your education. These are our tectonic plates. And I think at some point you learn there's like 9 or 12. There's actually quite a few, but lots are very little. Others, like the Pacific Plate, are quite large. As these plates move around, their boundaries interact in 3 ways. So there are really only 3 types of boundaries between our plates. Transform boundaries, where the plates are sliding past each other. Divergent boundaries, where the plates are moving apart, such as at mid-ocean ridges. A nice transform boundary example would be a transform fault out in the ocean, or the San Andreas Fault in the western US. And finally, we have convergent boundaries. So this is where the plates are moving together. And I'm going to focus on convergent boundaries. This shows a global distribution of convergent boundaries. Now, in the syntax geologists use, convergent boundaries are shown with this sawtooth pattern. So we have the Alps as a convergent boundary, the Himalayas as a convergent boundary, Sumatra and Java as a convergent boundary, the Andes in South America. The United States has 2 convergent boundaries. We have the Aleutians, right, up in Alaska, and then we have Cascadia. So we're going to hit on Cascadia later in the talk. Now, we can think of these convergent boundaries as continent-continent collisions building large mountain belts, such as the Himalayas. And then we also have convergent boundaries that we call subduction zones. So obviously, based on the title of my talk, I'm going to be focusing on subduction zones. And in particular, there are 2 in-member models for subduction zones. One in which the oceanic lithosphere is subducting beneath continental lithosphere, and one in which the oceanic lithosphere is subducting beneath another piece of oceanic lithosphere. So the one that's subducting is denser than the one that is not subducting. Now in this ocean-ocean convergent margin, you get things set up like island arcs. So the Marianas would be an example. The Marianas Islands would be an example of an island arc, or the Lesser Antilles down in the Caribbean would be an example of an island arc. So these two end members can be also viewed in this way. So the oceanic lithosphere subducting under a continent, we can call a Chilean type margin. And then I mentioned this before, the island arc situation, we might want to call a Marianas type subduction zone. Now, the Marianas type subduction zone also includes this old, thick, dense lithosphere subducting pretty steeply under the oceanic plate. Whereas in a Chilean type margin, you generally have younger, thicker, more buoyant, so less dense oceanic lithosphere subducting under the continent. And what this results in is a shallower dip to the subduction zone and a shallower dip to this place that we're interested in today called the subduction megathrust. So we're really interested in the plate interface from the trench to about 40, 50, maybe even 70 kilometers depth. And it's this type of margin that generally generates our largest earthquakes. So subduction is very important. It's part of the mantle convection system. Here we show oceanic lithosphere subducting well into the lower mantle. Subduction and arc volcanism are great water recyclers. So the plate has water in it, goes down into the subduction zone. Some of that water comes back out the volcanic arc. Some of that water goes into the mantle. Subduction and arc volcanism are actually very important for helping build continental crust. These are aspects of subduction zones I am not going to dwell on because this is the point of my talk. Subduction megathrust faults generate great magnitude 8 and above earthquakes and tsunami. So these are disturbing, shocking pictures showing some of the damage that these types of earthquakes can cause. So let's start back in time with 1960. This shows damage from shaking related to the earthquake in Chile. And then that 1960 Chilean earthquake, like other large magnitude 9 subduction earthquakes, generates a large tsunami. So this is damage in Hilo, Hawaii from the tsunami that initiated at the source of the 1960 Chilean earthquake. Now Hawaii gets damage from all sorts of subduction zone earthquakes. It gets the tsunami from Chile, it gets the tsunami from Alaska, it gets the tsunami from Japan. All right. So here's a picture of Alaska, 1964. This was another magnitude 9 earthquake. So this is some of the damage from the tsunami. We have tsunami damage from the 2004 magnitude 9.2 Sumatra earthquake, and shaking damage from the 2010 Maui, Chile subduction earthquake, and this rather mind-boggling picture of the tsunami actually coming into Japan in 2011. All right, so how does this work? Why do these subduction earthquakes generate tsunami? So here we have oceanic lithosphere subducting beneath continent. What happens is the plate interface shallowly locks and it pulls down the upper plate with it. Now that elastic potential is released in the earthquake. And I'm going to rerun this movie. And this time let's focus on the water. So during the interseismic, this period of time before the earthquake, the upper plate is actually pulled into the subduction zone along with the oceanic plate. And when the earthquake occurs, if it's big enough, it ruptures quite shallowly and displaces a large water column. And it's this displacement of the water column that leads to tsunami. So first of all, you have to have either a very big earthquake that ruptures quite shallowly to displace the water, or you can have a smaller earthquake that happens shallowly that still displaces water. But most subduction earthquakes occur back here, and so they don't necessarily, like the magnitude 7s and 8s, don't necessarily generate big tsunami. Okay? Now, if you remember back to our original map of where convergent margins take place, subduction zones are generally oceanic or offshore features, right? So the reason why you can get a tsunami is because the subduction zone, for the most part, lies offshore. Now, an earthquake starts at something we call the hypocenter or the focus, all right? And during an earthquake slip, right, the faults are, there's slip across the fault. The slip is going to spread out from that initiation point. Now, this involves a release of energy. So seismologists calculate something that we call seismic moment, and it's a measure of energy. It's simply, this is the only equation in my talk, all right? So seismic moment is simply equal to the fault area, so the depth and the length of the fault that slipped during the earthquake, some sort of average displacement, so how much the fault slipped. Did it slip 1 meter on average? Did it slip 30 meters on average? Did it slip 50 meters on average? So I'm going to talk in meters. I'm 1.6 meters tall, all right? I looked it up. I did the conversion. I'm 1.6 meters tall. All right, so moment is equal to fault area, average displacement, and rigidity or shear modulus. And you can think of rigidity or shear modulus as an elastic property of the Earth that relates how much force is needed to change the shape of a material. But the key take home is that moment is a measure of energy. Which brings us to one of my favorite slides. Subduction zones generate the largest earthquakes because subduction megathrust faults are long. Think of South America. Think about how long that subduction zone is. All right, so subduction megathrusts are long, which drives up that area, right? There's a lot of area. They're dipping. So again, that drives up the amount of area that can be involved. So subduction zones generate big earthquakes because there's a lot of fault that can fail. Now, how does this work out? On the left, we have magnitude. And magnitude, moment can be converted to magnitude. So think of magnitude as just being related to moment, like we talked about earlier. On the right, we have energy release in equivalent kilotons of TNT. All right. So on the left, we have earthquakes. And on the right, we have things that we might be more familiar with. So first of all, a good point is, this is earthquakes per year. About 1 million magnitude 2 earthquakes occur per year. Most of these are magnitude 2s we don't feel, all right? The 1960 Chile event was a magnitude 9.5. The 1964 Alaska earthquake was a magnitude 9.3. The Sumatra earthquake in 2004 was a magnitude 9.2. And the Japan earthquake from 2011, which we all pretty much, it's hard to forget, was a magnitude 9, all right? So those types of earthquakes are rare, right? We see less than one of those per year. Now let's look at what this energy equivalency is. The average tornado releases has an energy of equivalency of a high magnitude 4 earthquake, okay? The Hiroshima atomic bomb falls in kind of the low magnitude 6 range, all right? The world's largest nuclear test comes in at about an 8, all right? So that's the energy equivalent of something like the Haiti earthquake. Or the Haiti earthquake falls in, actually down here, quite a bit lower. All right, so this gives you a feel for how much energy is actually being released in these magnitude 9 events. Now, when I say great earthquake, technically to a seismologist, that means any earthquake greater than an 8. But for this talk, we're really gonna focus on these magnitude 9s and then a little bit on the Chile earthquake, which was an 8.8. So here's the distribution of magnitude 8 earthquakes since 1990. The yellow dots are magnitude 8 earthquakes above 70 kilometers in depth. There are a few magnitude 8s that come in down in the 600 or 700 kilometer depth range. We have really no idea how you get a magnitude 8 earthquake at 7 kilometers depth. There's not faults down there. So if you ever want to wonder what you could spend a career studying, deep earthquakes would be a good topic. Anyway, so you can see that here all of these yellow dots are magnitude 8 earthquakes, and they are primarily associated with subduction zones, though you can also get significant large earthquakes like in other convergent boundaries, like up in the Himalayas. But let's talk about fatalities from an earthquake. What are the two big fatal earthquakes that you can think about in the last 10 years? Sumatra, right? What's another one that comes to mind? Haiti, right? Both Sumatra and Haiti involved fatalities over 200,000 people, all right? Haiti was not a subduction zone earthquake. Haiti was in fact a magnitude, I'm going to forget the exact calculation, but kind of in the mid to upper magnitude 7 range. It was a strike-slip earthquake. So fatalities don't necessarily scale with the size of the earthquake. In other words, the hazard is not equal to the risk. You know, Haiti had a very large fatality number because of the built environment and the socioeconomic features of their cities, right? But in 2004, the Sumatra earthquake occurred. It initiated in northern Indonesia, generated a big tsunami. Most of the deaths from the 2004 Sumatra earthquake are actually from the tsunami, right? So Sumatra was not a particularly prepared society, whereas Japan, they had a magnitude 9. They had a number of deaths, like 25 or 30,000 deaths, I believe, but that was a prepared society, right? So they still lost, what was horrible number of lives, but it could have been much worse. All right. So subduction zones lie offshore, and the NSF GeoPRISMS program, which is hosting my lecture today, was developed to provide a place at NSF where geophysicists and geologists could go to get funding for onshore-offshore studies. So in order to really study subduction zone, you have to work out in the ocean and you have to work on land. So GeoPRISMS investigates the coupled geodynamics, Earth surface processes, and climate interactions that build and modify continental margins. So it's interested in subduction megathrust earthquakes, submarine landslides, tsunami, coastal subsidence, volcanic activity, things of that nature. It works under two broadly integrative initiatives, subduction cycles and deformation, which are obviously interested in subduction zones, and rifts. So my research really falls under this subduction cycles and deformation area. So what does this mean? Well, for one thing, this means that at some point, hundreds of scientists interested in the subduction zones got together and identified what are the key unknowns that we would like to know about, in this case specifically, subduction megathrust earthquakes. So a relevant SCD key question to the rest of my talk is what governs the size, location, and frequency of great subduction zone earthquakes, and how is this related to the spatial and temporal variation of slip behaviors observed in seismogenic zones? Now let me explain that last part. That's what this figure is meant to do. All right, so here we have a figure. On the y-axis we have log characteristic duration in seconds. How long does a signal last? An earthquake doesn't last very long. So we have signals that don't last very long, signals that last up to a year. All right, so some slip process that takes over a year to reach completion. Versus our new number that we now know, seismic moment. All right, so if we take a regular earthquake, and subduction megathrust earthquakes are not unusual earthquakes, they're regular earthquakes. Regular earthquakes fall on this scaling line. So they don't last very long, but the bigger they get, the longer they last. So rupture during Sumatra took about 500 seconds, for example, to go 1,300 kilometers. Now, there are a whole host of new signals that we've seen in subduction zones using seismometers and geodetic data. So the rise of GPS has enriched our knowledge of subduction fault processes greatly. And in particular, I want just to teach you all a little bit about something called episodic tremor and slip. All right, so episodic tremor and slip is one of these slow processes. It takes about a month to complete, and by the time this episodic tremor and slip is done, it has released a good amount of seismic energy, so magnitude 7 or 8 equivalent of energy. All right, so here's another movie. Before I start it, just want to orient you. So we're going to have our subducting oceanic plate. We're going to have our continent. This is basically based on Cascadia. This is a GPS station. These are all GPS stations. And then as the movie runs, so interseismically, you're going to see how this GPS station moves relative to some station that's well off into the North American continent. So the locked area represents our subduction megathrust fault. Down here we have freely slipping lithosphere subducting under other lithosphere. And then we're going to concentrate on this transition zone, and that's where this episodic tremor and slip develops. And I'm going to start the movie instead of forwarding my slides. All right. Is it running? All right, here we go. So we have the oceanic plate slowly subducting, and let's see, when does it start? So the relative motion before an earthquake is that both the upper plate and the lower plate are moving down up in this area, and then the expected signal is happening down here. Now, this GPS every 14 months in Cascadia is recording an unusual time period in which the plate doesn't release or doesn't fail in an earthquake, but the upper plate actually moves up like it would during an earthquake. All right? So what this results in is this GPS sees this little sawtooth pattern where it's moving to the east at a certain rate, and then for about a month it switches and moves to the west. Okay, so when I say slow faulting processes, this is what I mean. That for a month or a year, the fault is actually failing just like it would in an earthquake, but there's not actually an earthquake. So it's releasing the energy in another way. So let's talk Sumatra. We call this portion unzipping the Sunda subduction zone. All right, so here's Indonesia. This is the island of Java. This is the island of Sumatra, Malaysia, Thailand. We call this the Sunda subduction zone. And each of these beach balls represents an earthquake. Now I'm going to show a lot of these beach balls, so you have to forgive me as I deviate for a few minutes to tell you what seismologists use beach balls for. These are actually called focal mechanism solutions, and we use them to represent motion along the fault. So it's really easy to visualize this using strike-slip earthquakes. So you have two plates, you have some sort of, they're sliding past one another shown here, and there you have your fault. Now, if you take that fault and you imagine putting it into a tennis ball or a beach ball that's been cut in half, and you look down on it, which is the lower hemisphere projection fault part, you see a line. Now, earthquakes are double couple, which means that any fault that is at 90 degrees would create the same sort of compression or tension at various seismic stations. So that's why we always have two lines. So one of these lines represents the fault plane, and the other is called the nodal plane. Sometimes it's easy to figure out which is the fault plane and which is the nodal plane, and sometimes it's not so clear. So strike-slip earthquakes are beach balls that look like this. They have two little quadrants of compression, and so compressional quadrants. So again, where the fault is pushed material forward in our transform fault example are colored, and then two quadrants of tension, right, where stuff's been pulled apart. Now, most subduction megathrust earthquakes are pretty clearly reverse or thrust faults. And so in that case, their beach ball is going to look like this. There's going to be a lens-shaped pattern where the compressional quadrant is actually filled in. All right, so reverse faults kind of look like eyes, right, with the color in the center. Normal faults would be the opposite of that. So let's move back to this again, unzipping this Sunda subduction zone. So I've also color-coded these. So any of the red beach balls are actually subduction seismogenic megathrust faults or earthquakes. These black focal mechanisms are strike-slip events or some sort of complicated oblique intra-oceanic plate events. And then really shallow subduction megathrust faults or megathrust earthquakes are colored yellow. So these yellow focal mechanisms represent earthquakes that generate larger tsunami than would be expected just based on the amount of energy released in the earthquake. And this is because, in part, simplified, because they occur so shallowly. So even though the earthquake's not that big, it still displaced significant water column. All right? So we knew that the Sunda subduction zone generated large earthquakes. It's probably a little hard to see from the back of the room, but there were significant magnitude 8s in 1830, in 1797, and in 1860s. All right? What we didn't realize was that this portion of the subduction zone could be involved in one of those big earthquakes. So that in 2004, the magnitude 9.2 initiated here, just off the north coast of Sumatra, and it ruptured to the north. 1,300 kilometers of fault failed over 500 seconds. It was followed a few months later by another magnitude 8 event in 2005, because this occurred in December. So just a few months later, we had a magnitude 8.6 just directly to the south. And then in 2007, there was a magnitude 8.4. In 2010, there was one of these tsunami earthquakes that actually killed more people than the 8.4 did. And then finally, in 2012, there were these two large magnitude 8 events out in the oceanic crust. All right. So one of the seismological technique advancements that occurred when the 2004 Sumatra earthquake occurred is called back projection. So by 2004, the Japanese had put hundreds of seismometers out across their island. They know they sit on top of a subduction zone. So seismic hazard and risk assessment in Japan is hugely important to their society. All right, so back projection is a way of figuring out where the most energy comes from during the earthquake. So let's see if I can, did I lose my internet connection? Well, I guess we'll watch this movie. So this was actually Back projection was developed by Miyake Ishii while a graduate student at UC San Diego. She's now a professor at Harvard. I was going to show you her original back projection results for the 2004 Sumatra earthquake. But instead, back projection is now a cottage industry. So I'm going to show you the back projection movie put together by Alex Hutko at the University of California, Santa Cruz. So red indicates large amounts of energy. So what you're watching is the earthquake develop. All right, now it's been slowed down. The earthquake took about 500 seconds. This movie doesn't run for 500 seconds. But what I want to show you is the complexity of slip during the earthquake. So you're not talking about 1,300 kilometers of fault that failed at 4 meters across the entire fault length, right? There's a lot of complexity involved in these earthquakes. You know, it initiates down here, but most of the slip occurs to the north. And then there's segments where it dies out, and then there's another pocket where a lot of energy is released or slip on the fault is higher. So we can think of this in terms of time as a moment rate function, and that's what Alex is showing down here. He's showing in seconds how much energy is being released over the course of the initial earthquake rupture. So we call these moment rate functions. And when I showed that slide about duration earlier, that's where we would get that duration measurement from, is from these moment rate functions. So now we can do this with every earthquake. A big earthquake occurs, you can go online and watch these back projection videos of how energy is being released during the earthquake within a day. If you have the right Facebook friends, you can see it within an hour, right? It's pretty amazing. This took months in 2004. All right, so that was something we learned from the 2004 earthquake, was that northern part of the Andaman Islands could be involved in a magnitude 9. We didn't know that. We made great technological advances in the seismology community just to analyze earthquakes of that size, which comes to bear in 2011 when the Japan earthquake happens, because analyses that took months and months in 2004 literally were taking hours in 2011. Right. And then we really saw, again, I mean, we had seen it in the 60s, but we really were reminded again about the power of the tsunami. So 250,000 fatalities in 2004, most related to the tsunami. The tsunami had run-up heights of 4 meters, particularly in Banda Aceh. So Banda Aceh is a city that sits on that north tip of Sumatra. So here we have run-up heights of 4.3 meters in Banda Aceh, 1.7 meters, 3.1 meters in the South Maldives. And then we also see that the tsunami lasts longer than the earthquake shaking. So the initial rupture for the earthquake lasted 500 seconds. Then the surface waves rattle around, so the shaking related to the earthquake lasts a little longer than that. But the tsunami, so you can think of this as a wave coming out, a wave coming in, right? The scale on that is 120 minutes, right? So it takes a while if you're far away for the tsunami to reach you, but when it gets there, you feel it. Like there are multiple tsunami waves. It's not just one wave. A tsunami is multiple waves coming in, right? And this nice pretty image is actually a model of the Sumatra tsunami at hour 1:53, so at some point in the future. And it turns out there was a satellite that was passing over the Indian Ocean at the time, and so that satellite is called JASON. And so JASON, as it passes over the ocean, measures ocean height. And so what JASON was seeing, the red line here, was actually open ocean height related to the tsunami. All right, so that's what this model is trying to match. This model of where the open ocean height is highest and where the ocean open height is lowest, sometime after the earthquake was trying to match these satellite observations. Because at the time, in 2004, there weren't a lot of buoys. Right? That has also since been fixed. All right. So we have the 2004 9.2, the 2007 8.4, and the 2010 7.8, that's a tsunami earthquake. So I just want to show you the relationship to each other. So I've taken all of these dots represent aftershocks. I've taken a cross section through the 2004 region and through the 2007-2010 region. These are cross sections through those focal mechanisms. So all the red ones are again subduction megathrust earthquakes. So you have the main shock, but then you have a bunch of aftershocks. And the red bar above represents what I would term the seismogenic zone. So out to the trench to about 200 kilometers on the surface, right? It's a dipping plane, so this is actually longer than 200 kilometers. But the point is that the magnitude 9 really ripped through the entire seismogenic zone all the way out to the trench. Now this magnitude 8.4, which is a pretty big event, didn't do that. So the red represents the region of the fault that failed in the 8.4, and it had left this little portion, you know, this 70-kilometer portion all the way out to the trench. It didn't fail in the initial earthquake. Instead, 3 years later, that failed in what we would call a tsunami earthquake. So it was a subduction megathrust earthquake. It was quite shallow. It generated a large tsunami. Now let's look instead and compare that to what happened after the 2005 Sumatra earthquake. So the 2005 Sumatra earthquake was magnitude 7. It occurred just to the south of the 2004 earthquake. The white lines here represent the slip contour of the main shock. So that was what was involved in the original earthquake, and then you have all these green and purple circles that represent aftershocks. What this image is really focusing on is a signal that the geodetic data saw. So all of these red dots with the arrows are GPS stations. And after the earthquake, for quite a long time, they recorded something called post-seismic slip. So what they saw was you expect post-seismic slip down dip of the earthquake as the mantle kind of responds to the fact that the earthquake happened. But they recorded this large signal of post-seismic slip up dip of the earthquake. So in southern Sumatra, what failed as a tsunami earthquake 3 years later, just to the north, failed in one of these slow slip processes. So the energy was released, but over a much longer length of time, and didn't generate seismic waves like we would think an earthquake. All right? So there's a lot of variability in how slip is released just along Sumatra, just over this last seismic cycle. All right, and then finally, we have these two large magnitude 8.6 earthquakes that occur in the Oceanic Plate. So this slide is taken from IRIS, Teachable Moments. It was developed a few hours after the earthquakes occurred. These were strike slip earthquakes, and what IRIS has put on here are little yellow lines that represent that there's these old faults in the ocean plate that line up with what we would then interpret as the major fault, the north-south oriented fault involved in this earthquake. However, that was our gut reaction. Well, okay, these are the largest intraplate earthquakes we ever have seen. Who knew that the oceanic crust could fail in such a way? But then when you actually start plotting the aftershocks are all over the map. So in fact, the aftershocks are creating alignments that would suggest that it's the east-west nodal plane that is actually the fault that failed in one of the earthquakes. So you have the 8.6 up here, but then there's also aftershocks that are oriented on trends that are north-south. You have some aftershocks out here that seem associated with a smaller, a good size but slightly smaller earthquake. Then you have all these aftershocks out here that don't seem related at all to these. So it turns out when you watch back projection, or where the energy is coming from, this is the oceanic plate breaking in a series of faults. This is not two big north-south oriented faults. This is like taking a candy bar and bending it and watching the chocolate break up in a bunch of different orientations. That's what the oceanic crust was doing. So we didn't know it could do that. All right, so moving to Maui. So this is in the area of the earthquake that Charles Darwin felt in 1835. The pink here represents the 1960 rupture area. There's some greens and yellows that might be hard to see that represent significant sized earthquakes in 1928. And then if we look, there's this gap, right? So we knew that this had failed in 1835 because Darwin felt the earthquake. So we called this the seismic gap and said there will be an earthquake there. So as a result, the French went and put in lots of GPS stations. So we have all sorts of data, GPS data, because we were kind of expecting an earthquake to occur here. And it did. But it was a lot more complex than we were thinking it would be. So this is the magnitude 8.8. Significantly, it generated this big normal fault aftershock. It actually had a lot of shaking and caused, in some areas, more damage than the main shock. But my take-home message for Maui is, does interseismic plate coupling, or can the GPS data tell us in advance which areas of the fault are most locked and hence will have most slip during an earthquake? So this is just a place map again. Maui is here. This is interseismic plate coupling. So the darker the red, the more the GPS data was telling us the plates were locked together, right, at plate rates. So we know how fast the oceanic crust is coming in. We can calculate what the strain rate should be. Then we can compare it to what actually failed. Now, I know you can't see this from the back. So the colors here and the colors here are the same. They just have different contour breakoff. The blue line represents where the seismic data told us slip was greatest. So if interseismic plate coupling, if the GPS data is really predictive, then we would expect that these areas that are almost black will be the areas that failed the most. Of course, it's more complicated than that, right? The seismic data showed more slip in areas that weren't as black, right? So I think that GPS data is highly important. This still does tell us a lot about how plate locking occurs, but there are some discrepancies that need to be resolved between the geodesists and the seismologists. All right, so go a little faster here. We have Tohoku, we have Pacific Plate subducting beneath this little piece of North America, offshore northern Japan. What we learned from the Japan earthquake was that you can get a large magnitude earthquake in a pretty small space, all right? So Sumatra was a magnitude 9.2 over 1,300 kilometers. So long fault, big earthquake. Japan actually, so 350 kilometers, still a magnitude 9. And that's because along some portions of the plate, or along the fault, maximum slip was 50 meters. 50 meters, right? That is 40 of me. The fault failed, like, think of that in terms of a football field, right? It's something we can all visualize. 40 meters, or 40 or 50 meters of slip, all right? Let's compare that to Chile. So Chile, the darker reds indicate 24 meters of slip, right? So magnitude 8 magnitude 8.8 versus magnitude 9. The other take-home message from Japan is that if you know you sit on a subduction zone, you should be prepared. But even if you are very prepared, things such as a powerful tsunami are going to affect you, right? Here's that image of the tsunami coming in again. Here's fires and houses and debris, right? We're still getting debris from the 2011 Japan tsunami on our own west coast, right up in Oregon. They'll still find tsunami debris. So why does it matter? Japan was prepared. But we too have this hazard, right? We've seen it in Alaska in 1964. And we know from paleoseismic records and Indian myths and the fact that the Japanese recorded the tsunami that Cascadia has also hosted a magnitude 9 earthquake. And in fact, if you took our Cascadia and compared it to Sumatra, from what was involved in 2004, it's about the same scale. All right? So in Cascadia, we have hazard from subduction zone earthquakes, but we also have hazard from earthquakes that occur in the Oceanic Plate and in the upper crust. And those shouldn't be disregarded. They're just not the focus of this talk. So when a big earthquake occurs, it causes a tsunami, but it also disrupts the seafloor. So if it causes a landslide and all of that sediment gets mixed with water, you can get these large flows that travel large distances called turbidites. All right? So then if you go and core up and down Cascadia, you can start dating these turbidites, and if you make the assumption that they're related to the earthquakes, you can start to get a feel for the recurrence interval of these magnitude 9 earthquakes in Cascadia. So Chris Goldfinger at Oregon State has done this. He's found full, or what he calls full or nearly full rupture events. He's found 19 of them. So these would be magnitude 9 type earthquakes. But he's found he's found smaller earthquakes too. So 3 or 4 events that involve 3 segments of Cascadia. So he's broken Cascadia into 4 pieces, basically. And each piece has a slightly different recurrence interval, or when it was involved in an earthquake. So, the southern piece fails more frequently than, say, this piece under Seattle, which seems to only be involved in an earthquake every 500 years or so. Turns out that segmentation can also be seen in the recurrence interval of this tremor signal that's been seen in Cascadia. So here, these are all stations that record tremor, and they're color-coded by recurrence. So when tremor was first noted in Cascadia, it was noted up on seismic stations near to Seattle. It had a recurrence of 14 months. Then people started looking for tremor up and down Cascadia. They found areas that had recurrence intervals 10 months, areas that had recurrence intervals more like 20 months. Right? So you could actually segment Cascadia based on tremor recurrence interval, and that actually agrees quite well with the paleoseismology record that came after. The other interesting thing is based on thermal modeling, we know a lot about Cascadia. We have estimates about what's locked. Turns out in Cascadia, though, what's locked is really far offshore, and we're only now in the process of developing ocean bottom GPS, all right? We have ocean bottom seismometers, but we don't have really a good way to do our geodetic studies offshore yet. So we have what we consider the locked zone. We have this transition zone where we think like during a big event, rupture might propagate down. And this gives us what we call the down dip limit, which greatly affects the amount of shaking felt on land. So we have an estimate of the down dip limit for rupture in Cascadia. Well, now tremor, we've known about tremor for about 10 years. Each of these dots represent tremor locations. It turns out this tremor zone really lies just down dip of what we think of as the tremor, as the transition zone. So there are some discrepancies, but one big question is, does tremor, which happens in most subduction zones under land, if you have enough high-quality recording stations. Is tremor a signal that can be seen in every subduction zone? And if you can measure it, does it actually represent kind of the down dip limit? So do we have a better way of estimating hazard with a signal that we can actually measure? This is modeled based on temperature considerations. This is data. Data is always better, right? I do a lot of modeling, but data is always best. So in summary, each new earthquake has brought us more insight into how the seismogenic zone works. We've seen that fault complexity may be related, so these are more current models. So one idea is that this fault complexity, this regular earthquakes versus slow earthquakes versus tremor, may be related to variable frictional stability conditions along the fault. So that's kind of what's shown here. Instead of thinking of the fault as, two pieces of material put together where everything happens just evenly, let's make it more complicated, where you have these big asperities that might fail in a big earthquake. Then you have these little areas that might be generating your littler earthquakes or your aftershocks. Then you have this conditional stability regime that might rupture, but is in some place where you would initiate an earthquake. And then down dip, you have these slow slip and tremor processes. And if the same sort of slow slip process happens shallowly up dip, you might get like the after slip seen in Sumatra or even these tsunami earthquakes. All right. But the other thing we can't discount is that fault behavior might vary from cycle to cycle. So what was a tsunami earthquake in 2010, a few hundred years from now, when another magnitude 8 earthquake occurs, it might in fact be a magnitude 8.8 and rupture all the way to the trench. So what we think of as a region that only generates slow processes now, if the earthquake's big enough, it actually might be involved in the main shock, right? So we really have a problem with how much we see with these bigger events because they don't happen very frequently, and we really would like to have multiple seismic cycles. So obviously I pulled a lot of papers. So anytime I pulled somebody else's figure, it was cited in the talk. I just want to acknowledge you all for inviting me, but also GeoPRISMS and the program before GeoPRISMS, which was called the Margins program. Here's a list of some of my collaborators at all the universities that I've been to over time. And the final image I want to leave you with, and again, I apologize for the small fonts. This is a pie diagram showing energy release in all earthquakes across the world. And it turns out that if you go from here to here, that represents 6 earthquakes. So over half of the energy released in earthquakes since the last 106 years can actually be contributed or attributed to only 6 subduction megathrust earthquakes. 6. Chile, Alaska, Sumatra, Japan, Kamchatka, which I didn't talk about, and then a little slice here is that Chile magnitude 8.8. All right? So it's pretty significant. I do like questions.
What's the length of the record for the turbidite records?
Oh, how far back does it go? I don't remember offhand. Though Chris Goldfinger actually has a really, he has publications. This is actually just pulled from his website. He just goes on for pages. So there's lots of information on his website.
Anything else? Dr. Blanchard?
You and I have both lived along the New Madrid Fault. I'm just curious, if that's not a subduction zone, how do you describe what's going on there?
So New Madrid is an enigma. So actually, I study subduction zone earthquakes, but I also study New Madrid. And New Madrid generated a series of magnitude mid-7s, right, in 1811 and 1812, 3 magnitude mid-7 earthquakes in an intraplate system far away from plate boundary deformation forces. And we honestly don't know why. We think it's related to the fact that there's an old rift system sitting under New Madrid, sitting under the northern Mississippi embayment, that has concentrated stresses and is essentially being reactivated. But there are old rift systems in our continental material all over the world. And so intraplate earthquakes also remain one of the grand challenges of seismologists. But right now, EarthScope, so an NSF initiative called EarthScope, which has 500 seismometers essentially starting in California and sweeping across the US, is being conducted in order to better understand the lithosphere and crust under North America. And understanding New Madrid is one of the key science goals of EarthScope. So in other words, we're going to have, in 4 or 5 years, we're going to have unprecedented images of the crust and mantle beneath New Madrid, and hopefully that will allow us to tease out how you get a magnitude 7.5 earthquake in the middle of the continent.
All right. Well, thank you very much.